Good morning, everyone. In this video, we're going to be starting on page 2 in the note packet to talk about continuity. So a function is continuous if its graph never comes apart, or you can draw it without lifting your pencil. So that's the definition that I like because it's easy to visualize. So first, if I look at this reciprocal function and I start tracing it with my pencil, can we draw the whole thing? And can I skip up to this section and continue drawing it without lifting the highlighter? No, I cannot. So that tells me that this is discontinuous. If I look at this happy little piecewise function and I start trying to draw it with my pencil or my highlighter, I also see that I can't do it or jump to this piece without lifting my highlighter, so this is discontinuous as well. Now, this function, this polynomial-looking function, we can draw the whole thing without lifting our highlighter at all, so this would be a continuous function. And those properties lead to some things with the domain, typically things like asymptotes or holes or undefined values. So folks, we're going to get into a more specific definition for discontinuous because there are two types of discontinuities that we can have. We can have a removable discontinuity, which means if I were to remove the hole or open dot, then the function would be continuous when removed. So typically, this applies to holes in our function or open dots. The second type of discontinuity is non-removable. And these are discontinuities that even if I was able to fill in the dot or fill in the asymptote, it would still be discontinuous. So non-removable can be asymptotes or holes. So now, going back to these functions, we are going to see how to classify the discontinuities. So looking at this first one, the reciprocal function, we would say that this is discontinuous. Why? Because it has an asymptote, both vertical and horizontal. Now, if we remove those asymptotes, can I make this function continuous? And the answer is no, because I still have those two separate swooshes. So my asymptote is my discontinuity, and we classify it as non-removable. Now, on this function, if I look at my discontinuities, I have this first hole, and I also have this second hole. So when I would get to this second hole, I actually jump down to be this closed dot, so I can't like skip over that open dot without lifting my pencil. So we're going to classify these two different discontinuities. The first one is a hole or an open dot. And this one we classify as jump discontinuity. And jump discontinuity is very common in piecewise functions. And it is always going to be non-removable. So a hole that is non-removable. Because even if I were to fill in that dot, there would still be a jump between these two function pieces and it wouldn't be continuous. Now, my second discontinuity is this open dot or hole at location number 2. Now, this hole we would classify as removable because if we were to define the function there, I would be able to draw that with a smooth curve at that point. So that second hole is removable. And our last function is continuous, so there are no discontinuities. So folks, let's go ahead and just do one more example with this. let's say I have a quadratic whose vertex is an open dot, which is a special type of function we'll encounter later. So first, is this continuous or discontinuous? Because when I hit that open dot, I'm not defined there, and I can't jump to the other function piece where it is defined, this would be discontinuous. Now, the type of discontinuity is we've got a hole or an open dot. And if I was able to fill in that hole, then would my function be continuous? The answer is yes. So that would be a removable discontinuity. So folks, continuous, we can draw it without lifting our pencil off of the paper. And discontinuous, we can have removable, like this one, where we can make the function continuous, or non-removable, which is usually going to be things like asymptotes, but it can also be holes of our function as well. Folks, in the next section, we're going to be talking about another key features of graphs, which is symmetry. Now, I don't like that this portion says even functions and odd functions. We're going to go ahead and cross off that function part, because even degree functions and odd degree functions are something we'll talk about with polynomials. This is really just even and odd symmetry of functions. So we're going to go ahead and see how these formal definitions apply to our functions. So our first one, even symmetry, means symmetric across the y-axis. And it doesn't just mean symmetric vertically, it has to be symmetric on the y-axis. So if I look at this first quadratic parent function, is this even? Can I fold it in half along the y-axis? The answer is yes. Looking at this absolute value function, is it symmetric across the y-axis, or can we fold it in half across the y-axis? We sure can. This other fun-looking function, looking like the cosine function, can this one be folded across the y-axis? Yes, it can. So these are all examples of even degree functions. Now, I think it's also important to look at an example of what a not even function looks like. So I'm going to go ahead and just draw a little example over here of a quadratic that has been moved over to the right. Now, can I fold this graph in half along the y-axis? No, the graph itself is symmetric, but I can't fold it in half directly down the center along the y-axis. So this one is not even. So that definition we got to be really specific on when we are using even symmetry. Now, to prove this algebraically, so to prove even symmetry, essentially, we want to prove that reflecting the graph horizontally doesn't change the function. So if I have a function, f of x, we'll call that my original equation. What we would want to show is that horizontally reflecting it, or taking the opposite of the x value, so horizontal reflection is on the inside with x, we would want to prove that these yield the same equation and thus the same function. So this is how I prove even symmetry algebraically. So let's go ahead and just take a look at this graph down here, and we're going to see what this graph would look like if it has even symmetry. If it's even, that means it has to be the same across the y-axis. So this point over here at -1, 2 would also be on the other side of the axis. Now, when I reflect that point, I multiply the x value by a -1, and that becomes a +1, 2. So I can curve up through that point. This point down here is roughly at negative 2.5 down to. So about over here-ish, so curving down and curving back up. And this is what even symmetry looks like. So this is important because I can actually show this with my coordinates as well. So if I put in the -1 as my x value, f of -1, we would want to show that horizontally reflecting that point or transforming that coordinate gives me the same output. So if I find f of -1, does it give me the same y value? So f of -1 gives me 2, and f of +1 also gives me 2. So this is a way I can use just one coordinate to say, hey, for those coordinates, we do have even symmetry. Now, comparing the coordinates isn't always a good idea because, for example, this could dip down way farther on this side, so it would be symmetric at those 2 points, but not for the whole graph. So on the problems below, we'll see how instead of just using a point comparison, we can compare the original function with a horizontal reflection of that function to see if the function is even. Now, even functions or even symmetry functions, it's not too bad to prove and it's not too bad to visualize. Odd symmetry functions are a little trickier. First, odd symmetry means the function has rotational symmetry about or around the origin. So rotational symmetry about the origin. And for that definition, just like this has to swivel across the y-axis, the rotating about the origin part is key here. So I'm going to go ahead and underline that, about the origin. Now, to picture this, if I look at this linear function and I picture rotating it 180 degrees, does it give me the same exact function? 90 degrees would take me here, 180 degrees would take me there, and we would see it does indeed give me the same line. For a cubic function, if I swivel that, it gives me the same function as well. This function we can swivel, and that, when I rotate it about the origin, would give me the same function as well. Now, if you're wondering, how on earth are we going to prove rotational symmetry? It's actually pretty slick. Because the rotational aspect, it's like, oh my gosh, we're swiveling 360 degrees or 180 degrees. How are we going to prove that? What we end up proving is that vertically reflecting the graph and horizontally reflecting the graph yield the same graph. So to prove this, we want to show that vertically reflecting the graph and horizontally reflecting the graph yield the same graph. All right, folks, so to show this, I'm going to look at this linear function first. So let's think about vertically reflecting this. If I vertically reflect it top over bottom, this piece will go down here, and this piece will go up here to quadrant 2. So this is what a vertical reflection does to our original line. So I'll go ahead and darken that original line. So here's my original line. Here's vertically reflecting it. If I horizontally reflect it, which means flipping left over right or going left to right, then this top piece goes over here, and this bottom piece goes over, this bottom piece over here goes over there. So if I reflect this graph horizontally, this over here, that over there, and we can see that a vertical reflection and a horizontal reflection yield the same graph. So to prove rotational symmetry, we prove that horizontally reflecting and vertically reflecting yield the same graph. And we could see this with this cubic function as well. If I vertically reflect it, top over bottom, this piece goes down here, and this piece goes up here. There's the vertical reflection. And if I reflect my original graph horizontally or left to right, this piece goes over here, and this piece goes over there. And we see that we get the same graph. So you can generally visualize the spinning yourself, but if we're ever not totally sure, we're going to be able to prove it algebraically using vertical reflections and horizontal reflections. So to do that, so to prove odd symmetry, we are going to show that f of negative x, which is the function when I do a horizontal reflection, is equal to negative f of x. And that is what doing a vertical reflection looks like. So that is going to be how we prove odd symmetry. So horizontal reflection gives the same as a vertical reflection. All right, so to show this with a point, I'm going to go ahead and put this as -1, -3. Now, if I put in -1 for x, then f of -1 should be equal to negative f of -1. So f of -1 or f of +1 should give me 3, and negative f of -1 gives me -3, and that would give me a +3 as well. So that would show, using that point, that it works in both directions. So just sketching what this rotational symmetry would look like, 1, 3 would be my top point up here. And then we go down to about here-ish, matching up with that point, and then back up. So that is what an odd symmetry function looks like when we spin it about the origin. And folks, if this part with the coordinate was confusing, because I do think this is a little bit weirder to understand, you can go ahead and ignore that because we're going to focus on doing the proofs algebraically. So folks, in the following examples, are the following functions even, odd, or neither? We're asking, do they have even, odd symmetry, or neither of those two symmetries? So folks, we're going to go ahead and start with this first equation, and this is a quadratic that has moved down 3 units. So we don't even need our calculator for this one. I can go ahead and just sketch that. At 0, -3, swoosh. Now, does this look like it has even symmetry? We can fold it in half across the y-axis, so that's going to be a yes. This has even symmetry. Now, let's say we wanted to prove it algebraically. So what we want to show is that if we apply a horizontal reflection to the whole function, that it will give me the same function f of x. So is the original, this guy, the same as horizontally reflecting it? And how do we horizontally reflect it? We apply a negative inside with the x. So f of negative x, that's what horizontally reflecting our function looks like. There we go. That's what horizontally reflecting it looks like, a negative inside with the x. So if I apply a negative inside with the x inside my quadratic, we would get the following. So what happens when I simplify this? Negative 1 squared is positive 1 squared. X is just x squared. So 1x squared is just x squared. Negative 3. So f of negative x gives me this. So does horizontally reflecting my function give me the same function? It sure does, because I got x squared minus 3. So this is the same as my original function. So this shows that horizontally reflecting it, boop, gives me the exact same function. All right, folks, so let's go ahead and I'm gonna change my camera angle here a little bit. There we go. Let's go ahead and look at problem B next. Now, this is a quadratic, but it's not in vertex form, so we can't really use our transformation rules. We can tell that it has a y-intercept of -2, but let's go ahead and type this in on our calculator to see what our graph looks like. So x squared minus 2x minus 2. Pew. And this is what my graph looks like. Now, we can just visualize this, that if I were to fold this in half across the y-axis, it's not going directly through the vertex, so this is not even. If I rotate it about the origin 180 degrees, does it have rotational symmetry? Definitely not. So I can tell visually that this one is not even and not odd. So we say that it has neither of those symmetries. Neither. So let's go ahead and move to our last problem. Now this one, when we go to type this in on our calculators, make sure you put parentheses around that denominator. So x cubed divided by parentheses 4 minus x squared gives me, this fun looking graph. So I'm just gonna go ahead and quickly sketch what this looks like. So we've got this kind of cubic looking piece, and cubics have odd symmetry. If I do that little swoosh down there and that swoosh up there, not a perfect sketch, but we can see how it definitely doesn't have even symmetry. I can't fold it in half like a heart and get the same thing on both sides. But if I rotate it 180 degrees, if you can picture swiveling it, it does look like it could give me the same thing. But because this isn't a super friendly graph like an absolute value or a quadratic, this one we are going to prove algebraically. So we are going to prove odd symmetry by showing that horizontally reflecting it and vertically reflecting it give me the same graph. So I'm going to go ahead and do a horizontal reflection first. So here my function is named h of x, so I'm going to use that h notation. So what is h of negative x? Well, if I put a negative in with x, that would be negative x cubed, and 4 minus negative x squared. So we need to simplify this expression. Negative 1 cubed is negative 1, so on the top we get negative x cubed. And then on the bottom, negative x following PEMDAS squared gives me x squared. So then 4 minus x squared, I get this function. So this is what horizontally reflecting the function gives me. So horizontal reflect. Now, notice this is different from my original function because we've got a negative on the top. But the point is not to prove that it's the same as the original function. We want to prove that horizontally reflecting it and vertically reflecting it give me the same function. So, folks, we have found horizontally reflecting it. Now I'm going to find out what negative h of x is. So I'm just going to take the opposite of that whole function. That's what a negative on the outside does, is vertically reflect it. All right, folks, so if this is what a vertical reflection looks like, and this is what horizontally reflecting it looks like, the question we need to ask ourselves is, are these two equations the same? Is having the opposite of x cubed divided by 4 minus x squared the same as having negative x cubed divided by 4 minus x squared? The answer is yes. These two expressions are exactly the same, so if horizontally reflecting it and vertically reflecting it give us the exact same equation, that is how we know that this has odd symmetry. And that concludes page 2 of our notes.